Hello everyone, and welcome to my presentation on taming computational complexity. My name is Manya Rezapour, and I'm from Computer Science Department. I've been working on network structures like this with nodes and edges. The edges are the lines that connect two nodes. Whenever we want to analyze any sort of connectivity, these networks are the perfect model. We can model people and their relationships using networks, where nodes are the people, and whenever two people know each other, we connect them using an edge. We can also model friends and enemies in a network like this with positive and negative edges. In this network, an essential question is whether enemy of an enemy is a friend. This seemingly easy question is fundamental in understanding the implications of positive and negative interactions that go beyond the social context. In this network, enemy of an enemy is a friend, and we call it a balanced network. But in many cases, we're dealing with networks like this one on the right that are not balanced. But an interesting observation here is that there are only a few edges that can be removed to make the network balanced. In here, if we can somehow destroy the friendship between Sarah and George, the network becomes balanced. We call these edges that needs to be removed frustrated edges. But the problem is that a precise analysis of many of these networks are not feasible due to the computational complexity that is beyond our most advanced technologies. To put that into perspective, the enumeration required for analyzing networks like this takes hundreds of years on the world's most powerful supercomputer running full speed. In order to find the frustrated edges, we can color the nodes using black and white. Then a frustrated edge is either a positive edge with different endpoint colors or a negative edge with the same colors on the endpoints. This way we can look for the node coloring that minimizes the total number of frustrated edges. If we represent the number of nodes with n, then there are 2 to the n possible colorings. In this network, we can color the nodes like this, which leads to one frustrated edge. But finding the optimal solution in non-trivial examples is difficult. Suppose that the three-dimensional space of this classroom is our space problem. Then finding the optimal solution is as difficult as hitting a static invisible target that can be potentially anywhere in this class. Here is an example representing New Guinean tribes and their positive and negative relationships. The red edges represents enmities between these tribes, and the green edges represents their alliances. In here we have 16 nodes. Therefore, there are 2 to the 16 possible cases to be checked by the computer. Here is another network representing a group of monks and their positive and negative relationships. In here we have 18 nodes. Therefore, there are 2 to the 18 possible colorings. So when we increase the number of nodes from 16 to 18, the number of possible cases to be checked will be increased by 200,000. And this phenomenon is what we call computational complexity. Many researchers in the past have attempted solving this problem in very small scales, like the problem space of a size of a shoebox. Their algorithms are based on a random search. This is like throwing a bouncy ball with infinite energy into a random direction. As it bounces back whenever it hits a wall, eventually we will hit the invisible target. However, these random search algorithms are not practical for a problem space larger than the size of a shoebox. Here we have 329 nodes, which means that we are dealing with a number so enormous that I can't even pronounce its name. My research looks ahead to the extreme limits of solving hard optimization problems, where enumerating the solution takes hundreds of years. We didn't have 100 years, but we had a determination to tame the complexity and solve the problem for large networks like this one, which represents the interaction map of a white blood cell. In here, we decided to start with 3 years of thinking, simulating, and experimenting in the hope of getting some discount on the remaining 97 years. In these 3 years, we discovered and took advantage of the hidden structures of these networks. Our main achievement is that using a standard university-issued computer, our algorithm can analyze very large networks in a few minutes. Besides making new computations possible, our algorithm is the only one that comes with a guarantee of solution quality. This is equivalent to building a machine that checks and verifies something much greater than the number of atoms in the universe.